thank the organizers to give me the opportunity to talk about architecture of rotating star-planet systems, or probably more in the context of this meeting, how does a planet affect the evolution of the stars? So just like a short summary, we start with a little introduction, then I will concentrate on the data analysis, showing some of the things that we usually don't show in meetings, because most of you theoreticians, so it's good to know what we are doing behind the scenes. Then the modeling, the SPEM code, comparing with observations, and some conclusions and perspectives. So, introduction, rotation periods against orbital period of planets. So, we have up to now around 4,560 planets, although it depends on which website you are looking for. The European seems to be more productive because it's around 4,800 than the American ones, but anyway, I'm here, so I took the value from Caltech. And well, in principle, most of the system has just one single planet per star, although as you can see in this plot probably, and I can do here for the people in Zoom, so I got. Anyway, so I will do the pointing. Most of the systems has just one planet detected. Most of them we have a bias towards close-in planets. That's because we are using transits, that's normal, so we will find easier those that are transiting faster. And we need to understand simultaneously the influence of the activity and stellar winds on the host stars. So that's a plot that's triggering a little bit this work, which is from McQuillan et al. 2013. And we see that there is planets missing at short orbital periods and fast rotating stars. Remember that normally planets will evolve something like that. And so in this analysis, we have, they were using KOI, so Kepler object of interest, confirmed or not, with robust orbital rotation periods and orbital periods. Orbital period should be rotation period. Anyway, so 737. So we shrink the sample to these 737 systems. So here, this line is the co-rotation line, and this just fitting on the low edge of this dearth of planets there. So, what's causing that? That's the main question that we have. So, can we reproduce this with ab initio simulations? Well, hopefully we'll have the answer at the end of the talk. So, the objective is, how is the evolution of the stellar rotation impacted by the presence of a planet? Can we explain this dearth of exoplanets around fast rotating stars? Well, we're going to try to answer to this question by using ab initio prescription of tidal, magnetic, and braking torque simultaneously to improve our understanding on the underlying physics. So to do so, we are going to use only confirmed planets. That's very important. We are also excluding all, well, not yet confirmed ones, of course, and we are excluding all multi-systems here. This is because we are, for the moment, able to model just one planet in the system. Of course, that's probably not completely true, because that means that maybe some of these systems will have a second planet that we haven't detected. So, well, we have to live with what we have for the moment, and this is what we have. And we will be using all the full Kepler mission dataset. And I have to say that we have already started to extend to K2 results, although it's not yet completely done. So, from the data analysis point of view, how we extract the rotation period. Solar-like stars have an external convective zone, so that's uplift from the sun, and due to the magnetism, they have spots. And when the spots just move over the outside part of the photosphere, as you can see here, that produce a modulation in the light curve. If we track this modulation, we can obtain rotation period of the star at the latitude where the spots are evolving. So we have a kind of average rotation period in the active latitudes. Of course, I haven't said it. I don't know what happened. Okay, that's wrong. So for hot stars that don't have external convective envelope, they also can measure rotation because there are some spots that are not magnetic, probably composition, etc. So we can be also checking. So first of all, we have the impressive data from Kepler. We have to do something with all these fluxes coming from the pixels. That's actually one of the, what we call imaget. That's a French word saying small image around one target. So the target is there, it's the green pixels. So the green pixels is the actual mask used by the exoplanet people to look for planets. They want the smallest possible mask around a star because they want to reduce the noise. More pixels means more noise because every pixel has intrinsic noise. But for our study, we need to have the largest mask possible. That's because what you want is to keep every single photon coming from the, or electron, coming from the star to minimize any systematic from the satellite. The stars are moving. You have to fix this mask for the full quarter that you are observing, or month if it's TESS. And therefore the stars are moving, the satellite is doing some jittering, etc. So you want to have the maximum power here. So that's the yellow pixels we have. And of course you have to remove everything which is coming from another star, like the red pixels that you have there. So once you have done this for all the quarters, for all the stars, then you can start your job. So we're going to use the Kepler seismic data set that we have produced. They are all in the mast. And this is typically one of the control plots that we have when we do our analysis to detect rotation. So in fact, we're using 3 different light curves prepared with 3 different filters just to remove mostly the contribution of the orbit of Kepler, K2 also. We use 2 different methods. So what we call the global wavelet power spectrum, which is just a wavelet decomposition that we project into the period axis, because it has been shown that it's much more reliable than the Lomskargol parallelogram, which is just there upwards. Then we also use the ACF, so the autocorrelation function of the signal, the light curve, which is, as you can see here in this case, what we call a double dip. So you have a small periodicity and then a big one. It's meaning, in fact, you have 2 spots coming 180 roughly distance. So you have a first periodicity, which is half of the rotation, and the second one, which is the big one, is the real rotation rate. That's important because if you do a Lomskargol parallelogram or the wavelet power spectrum, and you keep the highest peak, you will be biased by double of the period. So we also do a third method, which is just a composition of the first 2, and then we have a reliable rotation period. The problem is that you have, as we can see here, 3 rotation periods, 3 light curves, so we have 9 rotation periods, and we have to choose one. So how we do that? We do that by using a simple decision tree. That was, it has been done since nearly 10 years ago. This is an example of this decision tree, in which we have, for just one filter, you have the 3 rotation periods we have. If everyone agree, yeah, got 3, you have win. You have a rotation period. But this happens for a very few number of stars, unfortunately. So then you have a second case in which you have 2 rotation periods agree, and it's half or double the rotation period of the other one. So this you say, okay, I'm picking up the harmonic of the third one. I took the other 2. It's good. I'm safe. So I take the second. Then you have a bad one, which is none of the rotation periods agree with each other, none in a harmonic either. So, okay, that's good. Means you don't know what is going on in this star, so it's good. And so on and so forth. But we agree that we are in 21st century, and we can do some better things, as it has been pointed out this morning. So that's machine learning. So the idea here is that instead of using our 9 parameters from the rotation periods, we actually use 150, which is all the combination of all the parameters we have on all the fits of the rotation period, plus of the stellar parameters, and we do a random forest. So a random forest algorithm is just the same random tree decision tree that we see before, but we do that in a random way. So we are going to produce decision trees for a smaller amount of parameters, and then we let the algorithm to make the division of each parameter with a sample that we know the results. So we know all the parameters of the stars, here. So the X, Y, X, E, and all the labels, so the rotation period in this case. So we let the algorithm train and understand how it goes. It takes, of course, the cuts that produce the best result, and just iterate this for a number of iterations. So, in fact, we didn't do one machine learning algorithm. We did 3 of them. So the first one is being trained to say the rotational class if the star is rotating or not. The second one is telling us if there is a pollution. So, for example, a classical pulsator, a compact binary, they have clear signatures that we can identify. So we teach the algorithm to determine them and flag that this is one of those stars. And then finally, we have the third one, which is going to select the rotation period among all the combination that we have. We have tried and trained the algorithm with K and M stars, and we managed to have an accuracy of 95.3% with the random forest. And of course, it flags stars in which he is not completely sure of the answer, and this is the ones that we just visually inspect, and we can rise to 99.5 in this case, just by checking a small amount of the targets. So one thing which is important is that the machine learning only selects the rotation period among the 9 combinations we have. So we don't touch anything on the statistics. It's just a selection of which of the rotation periods is the good one. That's important when we want to do a statistical analysis after. So just a commercial break. That's like a YouTube video. So we have applied this to the Kepler sample, and we have produced 55,000 and something rotation period for stars. So you can go and look to the paper there. So that's an example of the vetting that we have when we want to check. So this is 20 days filter, 55, 80 days, and PDC, Predata conditioning. That's the data used for exoplanet research. And I'm showing this just to warning, usually. The PDC is done for exoplanet research, not for rotation research. You have to take this into account. As you can see here, some of the quarters are completely filtered out. Because although the PDC MS map is supposed to keep all the stellar signal, sometimes it fails, and you don't have any flag indicating if it has to be filtered or not. So you have to take carefully when you use this data. So now we come back to the planet. So that's what we have something like a week ago. So that's the number of planets, and these are some numbers which is important for us. So we have in Kepler 2024 planets in Kepler, which belongs to 1704 systems, and from there we have 1240 single planets there. From there we have reliable rotation periods for 317 compared to 356 from Aquilon, which only 222 in common. I have checked several of them, and I cannot see those periods, which is mostly stars with a long rotation period. So that's the actual figure of planets that we have. I have to start to speed up. So this is the model that we are going to use, which is a model that simulates the star with 2 layers. So the convective zone, the radiative zone, and with the first interaction, the torque we are going to analyze is the internal coupling. Of course, as this is a single structure like that, it's for a star with a mass below 1.2 solar masses. We add the torque from the winds. So just here we have the representation of the wind. You have to remember that there is the Alphen radius, which is a surface in which everything which is inside it's in connection with the star, and this is the part that will break the star, and everything that happens after the Alphen star phase, just the star don't know anything about. So the third torque that we're going to simulate is the tidal dissipation, which is the interaction between the envelope and the orbit. So just to go fast. So, well, the first one is that it's going to make a change in the shape of the star. The second one is precisely the braking or the acceleration of the planet. So if the rotation of the star is faster than the rotation of the planet, the planet will drag the speed of the star, and then it will brake. The contrary will happen if the star is spinning faster than the planet. Then the planet tends to spiral into the star. Although there are some differences. So there are two types of tides that have been what's how much? I mean, okay. Two types of tides, the equilibrium tide and the dynamical tide. I don't have time to explain them, so I go to the next one. And finally, we have the magnetic interaction, which is if we suppose that we put a planet inside the Alphen radius, then we'll interact magnetically with the system, as it's explained here. And then, depending on the type of star, one torque is going to be more important than the other one. That's the summary of what SPEM is doing. And we are going to solve these three equations. So it's the evolution of the angular momentum for the orbit, the convection, and the radiative zone. But just to show what happened with a planet which is inside the rotation line, that's what happened after. So in this first part, it's dominating, the torque which is dominating is a dynamical tide, and after the rotation is the magnetic one which is dominating. So that's just to show the stellar mass against the orbital distance. That's the orbital period, if you know just Kepler laws. But if you add, if we add the magnetic torque, this is how things are shown. And the important thing is that everything which is inside this line here, well, this part here, will be following magnetic interaction. So let's go to the observations. We do 7,000 SPEM models with mass. Well, that's the characteristics. We can go back into the details, and that's the actual results. So here is the results from McQuillan et al. 2014. This is the 2013. These are our actual results. That's the distribution here. You see the difference in the long rotating stars. And this is the three models. So we have just the model with the tides and wind. That's the model with a magnetic field of 1 Gauss, and this is the magnetic field of 10 Gauss. What you can see, that's the rotation periods. The distribution of the model should be the same. And this is the orbital periods that we obtain. And in fact, as you can see, we have an excess of planets there that we cannot explain. So the simple model, well, the model we are using is not able to explain the results. There is something that is extracting planets from there. We have changed a little bit the initial sample, and we have removed all the planets orbiting inside 1 day in the original population. And we have again the excess here, and all the planets that are there are right, those that have migrated into that direction. If we go to remove all planets that are inside 2 days, again, we start to populate here, but it's not yet enough. We can cut this and do it in different places. We can cut in 10 days, and I mean, with small planets, big planets, so we can make different things, but in fact, in all the cases, what we have is that there is something missing in the models, and I just need one more slide before you kill me. So, which is this one, the conclusion and the perspective. So, what is going on? We don't know. We have some ideas, which are explained here. One thing which has to be reminded is that in this modeling that we are doing, the planet is just one single dot. There is no evolution on the planet. So this is something that is missing, and we are working on that. There is also, if there is more planets in the system, there is something that can also play. But I'd let you with these conclusions, and thank you very much.
Frank? Yes. Can you hear me?
Yep.
So this reminds me a lot of the work done by.
Your name.
Oh yeah, sorry. Yeah, so my name is JG Zanazzi, CETA postdoc fellow. So this reminds me a lot of the work that was done by Eve Lee and Eugene Chang like 5 or 6 years ago. Yeah, so your model has a lot more ingredients. So how does your model compare with the results they had? And in particular, how does your model produce ultra short period planets?
So the easy answer for me is that I have no idea, because this is the part done for the other half of the team. So I don't know if Antoine is connected. Should supposed to be connected, which is the responsible of the models. If not, it's that he's simply sleeping in Paris. So yeah, I cannot answer the the details on the model.
Any other questions?
Hi, Rafa. Jim Fuller. You went through that last part a little fast, involving the short period exoplanets. Can you just go over again what the discrepancy was between the data and the models and what you did to try to fix it in this plot on the right?
Yeah, so the idea is we want to see what is the contribution of each of the torques in the shape of the systems, to see if there is one which is better than the other ones. So in fact, if you have a small magnetic field in the planet, or you don't have, you usually have exactly the same distribution at the end. So it's the, whatever color is this one, it's a blue something. And the red one, yeah, they don't choose the color for a colorblind people like me. So yeah, as you can see, they are mostly the same. And the one which is really changing is the dark blue, which is the magnetic one, which is here. So you are increasing, yeah. Here you are increasing the population here against those. So the magnetic torque is being very important for populating, I mean, for bringing planets from outside orbits inside the region. But you need quite big magnetic fields.
So what is the purple line? Is that?
The purple line is just the sum of all of them. And it's called unbiased because we have corrected from the fact that when you take the Kepler population, you only see part of the system. So you have to take into account that not all of them are transiting, etc. You have to correct somehow for this to have the full distribution compared to the one that have been simulated.
So sorry, the purple line is not a model. It's data. It's trying to correct for observational biases.
Yeah.
Okay, and how's that different from the gray bars?
The bars is just the population of the KOI system, I mean the planet system. So not the full distribution of rotation stars, is the distribution of the rotation stars containing one single planet confirmed.
Okay.
And the difference between the two is that one is R rotation periods and the other one is Macmillan, just for reference. And the main differences between the two is at the very long rotation periods.
Okay, so it looks like there's still kind of a discrepancy around 2 or 3 days where the models are predicting more planets than is observed.
Yeah, and then what is interesting, but it's we can discuss probably along the week, is when you divide it into small mass planet and large mass planets. You can see, for example, that for the massive planets, the torque that which is dominating is the tidal one, while for the small planets is the magnetic torque, which is dominating. And you see in the distribution that you're taking the same. Here you have all the three, here. Yeah, here you have the three are on top each other. So the magnetic torque is not doing any job there, different to the other ones. While here, the magnetic one is closer to the real, well, yeah, to the observed distribution. So you have, when you don't consider magnetic torque, you have much more planets than when you consider the magnetic torque, which is removing planets. But still, there's a big difference.
Okay, thanks.
Any other questions?
Hello, I'm Xin Xileng from Caltech. So when you do the machine learning for random forest, so 150 parameters sounds a lot. So is there any consensus by the random forest which parameter is more important, and are they sensitive to the hyperparameters? Thank you.
Yeah, so you can go to the paper and everything is explained there. You have a few pages explaining exactly that thing. But the main parameters, of course, are the rotation period, what we call the SPH, which is the magnetic proxy that you have. So the amount of activity you are taking into account. The effective temperature of the star, it's also important. This will also help deciding if the star is probably a classical pulsator or something like that, or it's a star with a convective envelope, things like that. And then the next sequence of parameters, I don't remember because there are too many. But yeah, we explain them in the paper.
We have a question over Zoom. Melinda, do you want to ask your question?
Sure. I'm very interested in the automated rotational analysis of stars. I've been doing this with clusters recently, and I'm curious if there's any effort to extend Rooster's capability to incorporate S and G type stars, and maybe why that wasn't included in the initial rollout.
Okay, so the clear answer is that in the commercial advertising I did, it contains everything. So from F, J, K, M stars, if I manage to arrive to it. So you have 55,000 stars with rotation periods there. And the reason why, I don't find it, yeah, it's here. So the reason why we split it in two is because the first paper, which is only the F and K, K and M stars, there was something like 25,000, and in fact we visual inspect all of them. And we didn't want to visual inspect 130,000 of J and F. This is why we stop the paper there. We do the machine learning analysis, and then we finish the analysis. That's the technical reason why we split it in two.
Okay, that's great. Maybe we should talk one-on-one. I'm really interested in what you did and whether we could apply something like that. So thank you.
Yeah, no problem.
There was another question around there. Yeah.
Hi, my name is Janos Stuber. I'm at Caltech. You flashed up a picture of, I think, some inertial waves propagating when you mentioned dynamical tides. What is the prescription for the tidal torque you're using there?
The tidal torque, I think, yeah. That one's?
Yeah, I was just curious. So
it's yeah, sorry.
The frequency-dependent response of inertial waves is quite complex. I'm curious what kind of prescription you're incorporating there.
So for both of them are works done in France, most of them, and it's from Stéphane Matisse and his collaborators. This is where the prescriptions are coming. For the wind is Sean Matt, 2015, and Victor Reville, 2014, 15, 16, something like that. But yeah, that's the references. But I can give it to you more precise one if you want.
Yeah, maybe we can talk after. Thank you.
I think unless there is a short thing, we are at the end of the session. So let's thank Rafael again for a very interesting talk.